What if the relentless river of time carrying us from a known past to an unknown future is merely an illusion? What if the arrow of time, which seems to point so stubbornly in one direction, is not a fundamental law of the universe, but rather a consequence of what we, as observers, are able to see? This question invites us to journey from the grandest cosmic scales down to the impossibly small realm of individual particles. It asks us to reconsider everything we think we know about cause and effect, about beginnings and endings. Yet the deepest laws of physics whisper a very different and much stranger story. We are born into a world defined by its one-way processes. A glass shatters on the floor, but we never see the shards leap back together to reform the glass. A star explodes in a brilliant supernova, scattering its elements across space. But we do not witness those elements rushing back to remake the star. This directionality, this forward march, is what we call the arrow of time. It is the narrative thread that connects every event. This arrow seems to be governed by a powerful principle, a rule that appears to hold sway over everything, from a cup of coffee cooling on a table to the ultimate fate of galaxies. This governing principle is known as the Second Law of Thermodynamics, and its central character is entropy. Entropy is often described simply as a measure of disorder or randomness. The second law states that in any isolated system, the total amount of entropy can never decrease over time. It can only stay the same, or, more likely, increase. This law seems to be the engine driving time's arrow. Looks so different from the future. A state of higher entropy. It is the reason why yesterday's order inevitably gives way to tomorrow's mess. And so, we perceive time as a story of decay and dispersal. We watch mountains erode, buildings crumble, and memories fade. The universe itself seems to be on a one-way journey from an incredibly ordered state at the Big Bang towards a final uniform state of maximum entropy, often called the heat death of the universe. This perspective is powerful, and it aligns perfectly with our everyday experience. But what if this experience, this perception of a one-way street, is hiding a deeper, more subtle truth about the nature of reality? To understand the arrow of time, we must first become familiar with its constant companion, entropy. Let us paint a picture. Imagine a brand new deck of cards, perfectly ordered by suit number. This is a state of very low entropy. It is highly organized and predictable. Now shuffle that deck just once. The order begins to break down. With every shuffle, the system moves towards a state of higher entropy, greater disorder. It is far more likely a shuffled deck will be randomly mixed than perfectly ordered. This simple example reveals the statistical nature of entropy. It is not that a shuffled deck cannot return to order, it is just astronomically improbable. There is only one way for perfect order, but countless trillions of ways to be disordered. The universe, an immense deck of particles, is constantly shuffled. It moves from less probable ordered states to much more probable disordered states. This is the second law of thermodynamics in action: overwhelming probability. You place an ice cube into a glass of warm water. The ice cube is a small region of order, molecules in a crystalline lattice. The warm water is more disordered, molecules moving freely. Inevitable, heat flows from the warm water to the cold ice, and the ice melts. The ordered ice molecules mix with the rest, and the system settles at a uniform, lukewarm temperature. Total entropy, overall disorder, has increased. We never, ever see the reverse happen on its own. Now, let us zoom in, leaving the world of melting ice shuffled cards behind. Let us travel down to the microscopic realm, the world of atoms and subatomic particles. Here, where the fundamental laws of physics play out, we find something astonishing. The rules that govern interactions of these tiny constituents are time-symmetric. That means the equations work just as well forwards as backwards. The laws themselves do not contain an arrow of time. They have no preference for past or future. Imagine filming a collision between two billiard balls. Imagine two atoms. Play the film forward. You see them approach, collide, bounce away. Run the film in reverse. Approach from final paths, collide, move back along their initial paths. This question is old. 19th century physicist Johann Loschmidt posed it. He said, "If every atom's motion is reversible, the gas's behavior should be reversible too." A gas expands to fill a container, increasing entropy. But there exist initial velocities that would make atoms gather back, decreasing entropy. So why do we only see expansion? Why does nature seem to forbid large-scale entropy decreases? The answer emerges when we see the gap between microscopic reality and macroscopic description. Time-symmetric laws apply to the precise state of every particle, exact position, exact velocity. But we never have access to that complete information. We do not track every one of the trillions of atoms in a gas. Instead, we measure bulk properties: pressure, volume, temperature. These macroscopic descriptions are coarse-grained averages. This is where the illusion of irreversibility begins. A single macroscopic state can correspond to an immense number of different microscopic arrangements. The connection between entropy and our lack of knowledge is one of the most powerful ideas in modern physics. This concept was formalized in the 20th century by Claude Shannon, the father of information theory. He showed that entropy is not just a measure of physical disorder, but also a measure of missing information, or uncertainty. The more microstates that could correspond to the macro state you observe, the less you know about the system's true configuration, and therefore, the higher its entropy. The second law of thermodynamics can thus be rephrased in a striking way. It becomes a statement about our knowledge. It says that as a system evolves, it tends to move into macroscopic states consistent with a larger number of microscopic arrangements. Because we are ignorant of the precise microstate, this evolution looks to us like an increase in randomness and a loss of order. The arrow of time, from this perspective, is not an objective property of the universe, but a consequence of the coarse-grained, incomplete way in which we perceive it. It is an arrow of increasing ignorance, Imagine a vast library containing every possible book. One book is a perfectly written story. All the other books are random collections of letters. If you pick a book at random, you are overwhelmingly likely to pick one of the gibberish ones. Similarly, the universe in its evolution is moving from a highly specific, low-entropy state, the single-story book, to one of the vastly more numerous, high-entropy gibberish books. It's not that the laws of physics forbid the gibberish from rearranging into a story. It's just that there are so many more ways to be gibberish. This information-based view of entropy changes everything. It suggests that if you could somehow know the exact position and momentum of every particle in the universe, the concept of entropy would lose its meaning. For such an all-seeing observer, the universe would be like a perfectly functioning machine, evolving according to time-reversible laws. There would be no arrow of time. The past and the future would be equally determined and accessible from the present state. The feeling of flow, of a past dissolving into an unknown future, is a product of our limited viewpoint. The past and the future would be equally determined and accessible from the present state. The feeling of flow, of a past dissolving into an unknown future, is a product of our limited viewpoint. The mystery of time is not a closed book. It is an open invitation to look deeper. This journey into the heart of time and entropy can feel abstract, but it touches upon the very fabric of our reality. It challenges us to see the world not just as a collection of objects, but as a dynamic interplay of information and observation. The ideas we have explored suggest a universe that is far more subtle and interconnected than it appears. If you find these concepts as fascinating as I do, take a moment to engage with them further. Pause to consider the implications. And if you enjoy explorations like this, which connect the cosmos to our own experience, I invite you to subscribe and join us for future journeys into the mysteries of science. The thought that time's arrow is tied to information has profound consequences. It means that every act of forgetting, every loss of a record contributes to the forward march of time. Our memories, which are stored information about the past, are what create a personal sense of temporal direction. We remember the past, but not the future. This asymmetry of knowledge, this informational divide, may be the most intimate experience we have of the second law. We are, in a very real sense, information processing beings swimming in an informational sea. Thinking about these ideas can shift our perspective. When you next watch cream swirl into your coffee, you can see it not just as a simple act of mixing, but as a manifestation of probability and missing information. You are witnessing the system move into a more likely, higher entropy state because you cannot track the motion of every individual molecule. The seemingly irreversible act is a reflection of your own macroscopic viewpoint. It is a beautiful, everyday demonstration of one of the deepest principles in the cosmos playing out in your coffee cup. So, let us continue our exploration with a sense of wonder. The universe does not give up its secrets easily, but by asking these deep questions, we expand our own understanding. We learn to appreciate the hidden layers of reality that lie just beneath the surface of our perception. The relationship between the quantum world and the classical world, between information and reality, between the observer and the observed, is where the next great scientific revolutions are likely to be found. The mystery of time is not a closed book. It is an open invitation to look deeper. The link between entropy and information becomes even more profound when we consider the role of the observer in quantum mechanics. In the quantum world, the very act of measurement, the act of gaining information about a system, can fundamentally change it. Before we look, a particle can exist in a superposition of many possible states at once. When we measure it, this cloud of possibilities collapses into a single, definite outcome. Information about the other possibilities is effectively lost to us, and this act of observation can look like an irreversible event. This suggests that the arrow of time may be deeply entangled with the act of observation itself. Perhaps entropy increases for us because we are constantly interacting with the world, making measurements, and collapsing quantum possibilities. Each interaction leaves us with a definite record of one outcome, while the information about what could have been is scattered and lost. Our reality, the one we experience, is a long chain of these irreversible seeming measurements. The arrow of time might be the trail of these collapsed wave functions we leave in our wake as we move through the quantum realm. Consider quantum entanglement. Two particles linked so their fates are intertwined, even when they are far apart. If you have an entangled pair and only observe one particle, your knowledge of the overall system is incomplete. The part of the system you are ignoring will seem to grow in entropy from your perspective. Some physicists propose the thermodynamic arrow of time emerges for any subsystem of a larger, time-symmetric quantum universe. We, as observers, are always subsystems. Therefore, the irreversibility we see, the breaking egg, the melting ice, the dying star, might be a shadow cast by our own limited interaction with the whole. The universe as a complete, closed quantum system may be evolving in a perfectly reversible way, like a timeless quantum computer processing information. But we, as parts within that system, can only access a fraction of that information. The entropy we measure and the time we experience are features of our particular, partial perspective. They are real for us, but they may not be the ultimate reality. We arrive at a place of profound mystery and hopeful curiosity. We began with the simple, everyday experience of time flowing in one direction. We journeyed through the statistical nature of entropy, the time-symmetric laws of the microscopic world, and the deep connection between entropy and information. The picture that emerges is one where the arrow of time is not a rigid, fundamental law etched into the cosmos, but rather a perceptual phenomenon, an emergent property that arises from our interaction with a reality far more complex than we can fully grasp. This perspective does not erase the second law, it reframes it. The law remains an incredibly powerful and accurate predictor of the world we experience. Engines will still run, stars will still burn out, and our coffee will still get cold. But understanding its potential origins in information and observation opens up new frontiers. It suggests that the boundary between the knower and the known, between mind and matter, may be more blurred than we ever imagined. The arrow of time may be pointing not from a universal past to a universal future, but from what is known to what is unknown. This leaves us with a gentle yet deep question. If the arrow of time is indeed a feature of observation, a consequence of our limited knowledge, then what is the universe like when no one is looking? In a cosmos without coarse-grained observers like us, would there be any distinction between past and future? Does a river truly flow if there is no one there to see which way the water is going? The universe might be a vast, timeless quantum state, a shimmering ocean of possibilities where the concepts of before and after have no inherent meaning. And so, we are left to wonder. Perhaps reality is a participatory symphony, and the flow of time is the melody that we, the audience, create by listening. Our very existence as information-gathering beings might be what crystallizes the timeless quantum foam into a story with a beginning, a middle, and an end. The mystery of time is not just a puzzle for physicists, it is an invitation for all of us to contemplate our own place in the cosmos. What is the true nature of the river we call time? And what role do we play in charting its course? Maybe the arrow of time isn't a property of the universe, but a shadow cast by our own observation. The mystery of time is not a closed book. It is an open invitation to look deeper.